Welcome everyone to the INQA seminar series. Today with us we have Elijah Pelofske from Los Alamos National Lab, and we're gonna hear something about QAOA. Let's begin.
Thank you. Yeah, okay. So let me just reorganize my Zoom. All right. So yeah, I'm going to be talking about a paper that we recently put out. The title is Scaling Whole Chip QAOA for Higher Order Ising Spin Glass Models on Heavy-Hex Graphs. All right. So QAOA is a quantum annealing or adiabatic quantum computation inspired gate model quantum algorithm. So it's a purely discrete algorithm, and it consists of first preparing some initial state and then applying P rounds or layers or iterations, however you want to think about it, of the alternating simulation of the phase separating Hamiltonian and the mixing Hamiltonian. And you have some freedom over choosing different phase separating Hamiltonians and different mixing Hamiltonians. So within each round, H sub C is applied first, which separates the basis states of the state vector by phases based on the cost function that you've chosen. So in this case, our cost function for our optimization problem is C, and it's accepting some spin vector of spins Z. Okay, and then next, our mixing Hamiltonian then provides parameterized interference between solutions of different cost values. The original QAOA proposal was, by this paper, a quantum approximate optimization algorithm. And that was basically using like on maximum cut problems using the standard transverse field mixer. And since then, it's been generalized to a number of different variants. So reference 2 here is kind of a generalization for considering other mixing Hamiltonians and other types of optimization problems. But the acronym stays the same, being QAOA. Right, so in order to run QAOA, we need to find these angles, beta and gamma, which are kind of our parameterization of our two alternating simulations of Hamiltonians. In particular, we need to optimize them in some way so that our expectation value that we get out of the computation is either minimized or maximized. So the angle finding procedure can be done with something like classical machine learning. Just like, for example, in a loop with some classical optimizer, running on a CPU that interacts with some quantum hardware. And this is typically what makes QAOA be referred to as a variational algorithm, a quantum classical hybrid algorithm. Importantly, though, you don't need to do that classical machine learning if you already have good angles. So there's a number of different ways that you can approach this problem of finding what those angles are, right? You can use some knowledge, some physics inspiration, some inspiration, say, from quantum annealing. And here in this study, we're going to be looking at a particular technique for getting good angles called parameter transfer. Okay, so concisely, the QAOA algorithm consists of the following components. We have some initial state. We have a phase separating cost Hamiltonian. In this case, it's just derived from our cost function quite easily, but it can be more complicated for other types of problems. And we have some mixing Hamiltonian. And in this case, we just use the standard transverse field mixer. And our initial state is just the ground state of the transverse field Hamiltonian as well. The next component is our integer p. This is the number of rounds or iterations that we run the algorithm. So then within each p, we have this vector of betas and gammas that are each length p, and those are the angles that we need to optimize. So as we add more layers p, we expect to get better evolution, kind of like extending the continuous computation time in quantum annealing. But the challenge is that at each p that we add, we have another angle that we must optimize over, which can be challenging. So the goal of QAOA is for it to be a good heuristic solver for combinatorial optimization problems. But there are many unknown factors in regards to like its implementation, its performance, different problem types. As I mentioned, there's a lot of different variants and ways that you can implement it. So here we are interested in understanding how QAOA scales with respect to the number of variables and the number of steps, P. And we are also interested in kind of the overall algorithm and the different, and that requires looking at the different subcomponents of the algorithm. So how hard the angle finding is, what the ground state sampling scaling is as a function of say N or P, or you could select some approximation ratio less than 1, for example, and see how well the algorithm scales in that respect. And you know, something like that, you may want to look at something like if we had optimal angles, you know, an ideal computation, what would that look like? Or you can also look at what happens on hardware, what happens when you introduce noise. So numerical simulations here for studying QAOA are extremely useful, but the problem is that they are generally limited to either very sparse problems or very small problems. So something like less than 32 qubits. So we're therefore interested in how QAOA performs on current NISQ processors, which have an increasing number of qubits, but are still quite noisy. So something like right now, there are processors that have on the order of hundreds of qubits. And so we're interested in QAOA performance on those devices, in particular because they can't be, those quantum states can't be computed by brute force computation, but there are tricks to be able to compute those circuits classically, which we actually use. So our primary contribution is that we use transfer learning. There's a number of different terms that have been used in the literature for this property, and it originates outside of quantum computing in machine learning. Where I believe the term is transfer learning. But in the context of QAOA, the terms like parameter transfer and parameter concentration have also been used. The idea here is that for some class of things that are somewhat similar, parameters trained on those problems will be more similar than they are different. And so we are not the first ones to have looked at transfer learning or parameter transfer for QAOA. Typically in the literature, it has been examined for things like maximum cut. And in particular, the interesting property about this that we utilize to great success here is that you can do something like learn some good parameters on a small problem. And in this case, something like 16 qubits, which it was very tractable to simulate classically. And then we use those exact same parameters on a much larger problem instance. And our performance is still very good on the much larger problem instance because the properties of those classes of problems are very similar, even though the size is very different. And yeah, so in particular, we optimize these QAOA angles using just a single 16 qubit instance, and I'll define what the optimization problem was in a second. And then we use those exact same angles to run on 127 qubits. So we verified that this transfer learning worked using matrix product state simulations. And we execute these QAOA circuits with these learned angles on several different IBM quantum processors. So the optimization problems that we consider have been previously introduced. We actually looked at these previously for looking at a comparison between QAOA and quantum annealing, which I actually gave a talk about a year ago at another INQA seminar. So those problems that we introduced, they are Heavy-Hex compatible. Heavy-Hex is the name of the connectivity graph that current IBM quantum processors have. It's a pretty sparse graph, and I'll show an example of it in a second. And on top of this, we add geometrically local cubic terms. So these optimization problems are sufficiently sparse, but have a large number of variables that we can evaluate the performance of QAOA by both increasing n and p using classical simulation, matrix product state simulation, and on IBM quantum hardware. Okay, so these two are an example of what these optimization problems are. These are Ising models. So here the ovals denote hyperedges, the cubic terms that are geometrically local to the heavy-hex lattice. The red and green coloring denote the sign on the coefficients of the optimization problem. So here we have, we randomly select the coefficients for all of the quadratic terms on the underlying hardware graph. That connectivity graph is the heavy-hex graph. And then we also randomly select the sign of the coefficients for all of the cubic terms. So on the left-hand side is a 27 qubit instance, and on the right-hand side is a 16 qubit instance. And these particular hardware graphs are actually hardware graphs for IBM processors that we ran these experiments on. All right, and then this is what this problem type looks like on the 127 qubit heavy-hex graph. So again, same use of the ovals to denote the geometrically local hyperedges. And this is again an actual hardware graph that that an IBM processor has. Actually, multiple IBM processors have these hardware graphs. Right, and again, previously introduced in our previous kind of comparison paper, the reason that we focused on these optimization problems, as you might imagine, it's because general, random, densely connected problems are decently hard to implement well on current quantum computers because the error rate is so high that if you need to, move around your problems too much, you have too many swap gates. Or just too many gates, period, the noise incurred will increase proportionally, right? So, so we constructed a QAOA circuit that can sample these hardware compatible Ising models very efficiently. In particular, the very interesting feature of these circuits is that we are able to address the additional cubic terms that are spread throughout like across the entire lattice with the introduction of only a single layer of single qubit gates. So we actually have no overhead of CNOT gates, and CNOT gates usually are the gates that have higher error rate, and they also take longer to implement on the hardware. So this is a very, very interesting, a very nice optimization. So our corresponding circuits that we get have a CNOT depth of only 6. So this is true for the entire lattice. So we can apply this construction algorithm to the entire lattice and get a very short depth circuit across the whole lattice. So in the components here, you can see on the left-hand side is what our lattice might look like. We have 3 edge colorability, and it's also a bipartite graph. The purple adjacent lines denote the cubic terms, and then on the right-hand side is what the corresponding circuit for this subportion of the graph would look like, where we show the 3 different edge colorings. And in terms of phases of the circuit, we have our initial state, then our phase separator, and lastly our mixer, which is our transverse field Hamiltonian. And then lastly, we measure the states of all of the qubits. And we expect that the resulting distribution that we get has an expectation value that we hope is good if we have optimized our angles well. Right, so the tool that we use, so in general, angle finding is decently hard. Like there's a pretty large number of approaches, lots of different machine learning approaches. And here we use a new tool, a pretty recent tool that actually our group at Los Alamos developed called Julia QAOA. It's based on Julia, or written in Julia. And we use this to get really, really good angle finding. This is, I think I can say this is the best QAOA angle finding tool I've yet used. And so in particular, we compute for each P on a 16 qubit instance, just a single one, we computed as good of angles as we could find using 1,000 basin hopping iterations. And if you're interested, this tool is actually publicly available on GitHub. I should note that this particular tool, we don't have any guarantee of optimality. This tool allows you to address arbitrary problems with a variety of different mixers potentially, but we don't know if those angles are optimal. What we do know is that the angles are very, very good, and good in the sense that as we increase P at each step, our mean expectation value improves, right? So these are heuristically good, maybe suboptimal angles. All right, so the other tool that we use in this study is matrix product state simulations. And here, so we're just able to compute the QAOA expectation value for a given set of angles. So again, this doesn't really help with angle finding necessarily, but it does allow us to evaluate what the quantum computation should be in a noiseless setting. So this is a tensor network simulation. So the accuracy of the MPS simulation is determined by bond dimension, here denoted by chi. And in general, we expect that the accuracy improves with growing chi. So we perform MPS simulations for chi equals 2 to the m, for m equals 4 up to 11. In particular, the goal there is to estimate the impact of errors to see what the convergence behavior of the MPS simulations look like. Interestingly, the MPS simulations become exact for P equals 1 and P equals 2 at chi equals 64 and 1024, respectively. One of the reasons that this is interesting is that previously, our best classical simulation method was using light cone-based simulations. Because the problem is so sparse, you can look at light entanglement light cone subparts of the problem and just simulate the mean expectation value there. And we were able to do that for P equals 1 and 2, but then past that, the entanglement grows too much. So using classical brute force across the entire, like enumerating through all of the subgraphs, all of the polynomial terms no longer works. However, here with MPS, we were actually able to go up to P equals 5. So the largest QAOA circuits we were able to do. Another very interesting and useful property here is that since MPS is a unitary tensor network, you can actually draw bit strings from a simulation. So that means that we're actually able to compute what the distribution should be in a noiseless quantum computer, given some angles. All right, so here is the MPS simulation for error convergence. So here we're using the error difference between the largest bond dimension we ran, which was 2048, compared to each of the lower bond dimensions. As expected, the hardest case is P equals 5. That is the largest circuit. And in general, we get pretty low errors. So we're pretty confident that we got good convergence here and that these are very good approximations for what the QAOA distribution should be. These solid black lines represent the error in the energy averaged over 100 instances. So here for all experiments, we look at an ensemble of 100 problems to see what happens to the aggregate. And all computed errors for all instances are contained within the gray regions around the black lines. And interestingly, at P equals 5, we actually see that the gray areas are becoming relatively smaller. And this indicates that the different instances of the optimization problems result in smaller errors. Okay, so here's the primary numerical result plots. So these are all of the numerical simulations showing QAOA angle transfer working. So on the left-hand side, what we're looking at is on the x-axis, we have increasing P1 up to P5. And then on the y-axis, we have energy. So here we're considering all of these Ising problems as minimization, optimization problems. And each of the blue lines, there's 100 blue lines. Each one represents a different problem instance. So these problem instances have the exact same connectivity graph, What's being changed is random choice of the coefficients. Okay, and again, all of these have the cubic terms. So what we've done is, on the left-hand side, we've selected one of those problem instances, and we've run Julie QAOA on it to get really, really good angles for P1 up to P5. And then we've used those angles to execute, or we've ran the QAOA circuits using those angles for all 100 instances. Okay, so one of those lines has the one that was trained on. And as you can see, so this is one of the nice things about parameter transfer is that, especially if the problem instances are like the same size, you will get very, very similar performance. And you definitely see some variation. But so parameter transfer worked for all of the 16 qubit problem instances. And in particular, what that means is that, we can use these angles for 100 problems. We don't have to retrain on all 100. And for 16 qubits, that's maybe not too bad. But as you increase in size, that computation expense increases. Okay, and then in the middle plot, what we've done is we've used those exact same angles, no changes, and we've run QAOA simulations for 27 qubit problem instances. Okay, so that's a bit of an increase. And again, we see a nice decrease in energy like we want as a function of P. And then on the far right-hand side, we've done the same thing, used the exact same fixed angles for 127 qubit instances. And this was in particular using the MPS simulations with a bond dimension of 2048. So here, all of these lines are just showing the mean energy, okay, not distributions. But importantly, as P increases, for all of these lines, the mean energy strictly improves, meaning decreases. So this shows that transfer learning succeeds in the noiseless setting across a pretty large ensemble of problems. All right, so here, these are the MPS sample distributions. This is the capability that I mentioned earlier. So these are for 3 different problem instances. These are all 127 qubit higher order Ising model instances. And each of the distributions is, P1 up to P5. And the dashed black line that's on the left-hand side of each of these subplots for each of the problem instances shows what the energy of the optimal solution is. And this was, we were able to compute this using order reduction on the problem and then running CPLEX. So CPLEX is not necessarily state-of-the-art for combinatorial optimization, but it was able to solve these problems very, very quickly, like order of seconds, less than a second, that sort of thing. And so we were able to, we use CPLEX as the tool to figure out where exactly the ground state is. And note, importantly, so here, each of the distributions are showing 8,192 samples. And again, this was using the largest bond dimension of 2048. And the thing to note here is that none of the MPS sample distributions found the optimal solution. And so what this actually means is that even in the noiseless setting, like, we need to go to even higher rounds of QAOA in order to get a good probability of sampling the optimal solutions. Okay, so here's our QPU summary table of all of the IBM quantum processors that we used in this study. So I'm not going to be showing plots for all of these, but there are plots for all of these in the paper. So on the left-hand side, we have the device name. Next, we have the processor type as named by IBM. Then we have the number of qubits, then the number of 2 qubit gate interactions on that hardware graph. Then we have what the basis gates are. ECR and CX are the 2 qubit gates. Next, we have a summary of the linear and quadratic term count, which are the same as the number of qubits, the number of 2 qubit gates, and then also the number of cubic terms. that can be placed for this problem type on that Heavy-Hex graph. Okay, so the QAOA circuits are compiled using Qiskit, mostly to adapt the gate set. The QAOA circuits have been extremely heavily hand optimized. And we use a fixed hardware graph. So the compiler optimization is not able to reduce the 2-qubit gate count. We also evaluate dynamical decoupling in these experiments just to see if that could help. We use a fairly simple scheme that's probably not optimal in terms of possible dynamical decoupling sequences. But these are just pairs of poly X gates. And we tried 2 different scheduling options. So same circuit duration, but whether the gates are executed as soon as possible or as late as possible. Dynamical decoupling is a type of open loop quantum control error suppression technique that can mitigate some types of error, but it kind of depends on like the noise profile on the device. And for each angle / parameter combination, we use 20,000 shots. So most of the plots that I'll show are showing mean distributions. And keep in mind that that's out of 20,000 shots. So these are pretty robust statistics. Okay, so here's the first experimental plot. So again, going back to our MPS simulation, in the noiseless setting, we know that as a function of P, we should be seeing improvement in energy. But what we actually see is degradation in performance as P increases. And of course, this is to be expected because we have some constant error rate on the hardware. As we add P, we incur more error. So here, each gray line represents a single instance with experiments run for P = 1 up to 5. And these same instances were run on all of the IBM processors of this size. So I'll show more plots in a second. The dashed black line is showing what the mean behavior is across that ensemble of problem instances. The green X marker shows the P that achieves the lowest mean energy for that instance. So the cluster of green markers shows where the tipping point is, right? Where the trade-off happens between noise in the computation and how good the QAOA angles are. And this particular data was run with no dynamical decoupling sequences. Okay, and now here's a very, very similar plot, but now it's on a different processor. The last one was on IBM Brisbane. This one is on IBM Sherbrooke. This is, again, mean QAOA energies for this ensemble of 100 problem instances. These are the same problem instances as the previous plot. And here, so we can see that kind of the aggregate of where the green ticks are roughly at P = 2 or P = 3. So that's roughly where the peak of performance is on these devices. And okay, and here's another 127 qubit instance plot. This one is on IBM Cusco. This one is notable because the performance is much worse compared to the previous 2. So here, the best performance was actually at P = 1. And the energy y-axis in all of these plots is the same. So if I go back one slide, you can see that IBM Cusco has much worse energy, even starting out compared to IBM Sherbrooke or Brisbane. All right, and here's a fourth plot. This is IBM NASCA, and here this performance is better. We see the peak is at about P = 1 or P = 2. At the time of running these experiments, these 4 processors that I've just shown results for were the only processors with 127 qubits. At this point in time, there's actually now more, as well as a 133 qubit device. Yeah. Okay, so this plot is showing same experimental setup as the first plot with IBM Brisbane, but here we've executed the QAOA circuits with dynamical decoupling scheduled as late as possible. And in particular, the reason I'm showing this plot, we have like many more plots in the paper, but I'm showing this because this was generally the best performing result that we found. Okay, this was IBM Brisbane with both ASAP and ALAP dynamical decoupling performed the best. So this is our best performing result, and you can see the maximum P on average was P equals 2, 3, and a little bit of 4. Right. So so those are the 127 qubit results, which are quite interesting because the qubit count is high, and so it's good to see what happens with the computation at that scale, right? Like what happens because of noise. But of course, our original parameter transfer studies, we defined these problem instances actually on just like the 16 qubit problem instance was defined on the IBM Q Guadalupe hardware graph. So we also have results for 16 and 27 qubit devices. So this is same style plot, but now it's a different problem instance, right? Energy scale is much smaller than it was in the previous plots. And IBM Q Guadalupe is the only 16 qubit processor at the time that we ran these experiments. Right, and you can see that the best performing P is probably P equals 2, maybe P equals 3, and there's like 2 outliers at P equals 5, which is kind of interesting. Right, and the other thing that I should note that's important for the previous 127 qubit plots is that the optimal energy here is about -200. It does depend on the exact problem instance, so there's a little bit of variability, but it's about -200. In the paper, we have a full detailed tables of the minimum energies sampled and the absolute minimum energies possible for the optimization problems. But so to give you a scale, right, this is less than halfway to the optimal energy. So the mean energy for these smaller problem instances is not as good, but of course the optimal solution is much closer to 0. So although although the means aren't necessarily great for all 116 qubit instances, the optimal solution was always found, which maybe is not to be unexpected, right? 16 qubit instance. But we actually observed the same thing for the 27 qubit instance. It's only for the 127 qubit instances where the optimal solution is never found by the IBM quantum processors. Okay, so this is showing a 27 qubit result, same style plot. This is IBM Q Mumbai. This is our best performing 27 qubit processor result. You can see the distribution of green ticks here is more right shifted, which is pretty encouraging. If we go to something like IBM Cairo, you can see that the peak of performance is at about P equals 2 or 3. So, not as good performing as IBM Q Mumbai. And IBM Q Kolkata, similar story. The peak seems to be at P equals 2. And as before, full ensemble of 100 problem instances. So generally the peak performance was at about P equals 2 or P equals 3 for most of these results. Okay, so the last thing that I'm going to mention is what is, I believe, the largest QAOA experimental demonstration in terms of number of qubits that has been performed. So this was done on IBM Seattle. So this was a 433 qubit IBM processor, but 19 of its qubits were deactivated, were not available to users. So we could only use 414 of those qubits. So as you can see, again, it's a heavy-hex graph, so we can apply the same Ising model problem type as well as QAOA circuit generation to this hardware graph. Now, the caveat is, and the reason that this is last in the slides, is that this device was decommissioned before we had developed our experimental methodology, in particular the transfer learning. And so the experiments that we have here are basically they're only on one round of QAOA, so they're not up to P equals 5. And because this was before we had the transfer learning angle finding capability, we just went with a like naive grid search, which is what we had done previously if we were not aware of what the best angles were. Now, interestingly, what we find in these angle grid searches is quite encouraging for parameter transfer. That is that we've looked at one round grid searches before for a number of different for these problem types, but for varying sizes of these problem types. So in particular, we've looked at like 27 qubit grid searches, 16 qubit, 127, and now 414. This is on hardware. So I'm not showing the smaller QAOA angle grid search plots in this. This is only the 414 qubit instance, but we see very, very high agreement, even on the noisy hardware, of basically what regions have really good angles and what regions have very bad angles, right? So basically where these blue regions are very consistent. And so that was very, very exciting to see. But unfortunately, we couldn't perform all the experiments we wanted on the device. Right, so the one important caveat with these plots is that on the right-hand side, the problem instance, we've actually taken out the cubic terms. So this is just a linear and quadratic polynomial Ising model. Whereas on the left-hand side, we do have the higher order terms. And so what we're showing on the x-axis is varying beta. The reason that search space is cut in half is because of symmetries in the problem that we can take advantage of. And then the y-axis is varying gamma. And this is a pretty fine grid search. And the heat map is showing the mean energy at that given angle. So this grid search was something like, I think, 6,000 different individual points, maybe 7,000. No, this is very exciting to see. Note also the property that's consistent with these problem types is this symmetry of kind of which side of that zero line the good versus very bad angles are. And so what we can do is we can look at what that sample distribution is for the best angles found on the IBM Seattle grid search. And so that's what these histograms are. Again, same setup as previously, where the left-hand side is the problems with the higher order terms, right-hand side is the problems without the higher order terms. So the important thing to note here is that first, the noise on IBM Seattle was pretty high. Like I think it was higher than, say, the single and 2 qubit gate calibration metrics for something like IBM Sherbrooke, which was one of the 127 qubit processors. But of course, the qubit count was much, much larger. So kind of the basic thing that you want to check is, is this distribution better than just a kind of random sampling, which would be centered at about 0 here on this histogram. So it is definitely better than that. That's good. And then the other thing that we want to look at is, say, where's the optimal solution? So this is a much larger problem instance. Previously, the optimal solutions for the 127 qubit instances were at about -200. Now they're at about -600. So we're pretty far away from the optimal solution, which is probably to be expected. And so again, for large hardware, we need kind of lower error rates and higher QAOA rounds. Okay, so this study is the largest, or comprises some of the largest QAOA demonstrations on quantum processors to date in terms of qubit count. And the size in terms of gate count is also quite large. And so this gives a sense for where QAOA is at for combinatorial optimization, especially on near-term processors. And in particular, we found that transfer learning of QAOA angles is a very effective mechanism to use. for running QAOA on quantum computers. And so we've used this technique to evaluate QAOA on problems with 127 qubits up to p equals 5 rounds. And these QAOA circuits can be pretty efficiently simulated using classical MPS simulations, and that's just because of how sparse they are. And this allowed us to also generate sample distributions to see what the noiseless setting would look like. And we found that even in the noiseless setting at p equals 5, we would not be able to sample the optimal solutions, meaning we need to get maybe even better angle finding, like better angles, maybe after we've done the transfer learning, and or two, go to higher rounds using more transfer learning techniques, higher rounds with good angles, or both. We found that the poly-X pair dynamical decoupling sequences improved the QAOA computations for some, but not all, of the IBM quantum processors. And this success also depended on the compiled hardware level scheduling. So in some cases, we did see a difference between ALAP and ASAP scheduling. As a very clear example, both scheduling options of dynamical decoupling improved the performance of IBM Brisbane, but interestingly enough, for both dynamical decoupling scheduling options actually made the performance on IBM Sherbrooke worse. So again, it just depends on the particulars of the device, and there's better dynamical decoupling sequences that could be used in future studies as well. And as expected, the additional noise in the computation, as we added more QAOA layers, overcame, the theoretical performance of adding higher rounds with good angles. Generally, the peak of performance for the quantum computers was at about p equals 2 or 3. And we used CPLEX to compute all of the optimal solutions after order reduction for all of the problems. So, this means that classical combinatorial optimization solvers can very efficiently solve these problem types, which again, not particularly surprising because of how sparse they are. So future studies should also look at harder problems, meaning more variables, more densely connected, and or higher order terms. For example, the IBM Seattle results that I showed, that's 414 qubits, but because they're so sparse, you can still use, for one round, for example, you can use something like MPS simulations to compute the QAOA performance quite well. You can also use the light cone entanglement simulation method I briefly mentioned earlier. You can also do that. You can do that basically on arbitrarily on large graphs up until you hit whatever the entanglement growth limit is. As long as the graphs are sparse, you can do that. So in this case, for p equals 1 and p equals 2, like even if you had 1,000 variable problem, for example. Right, and so out of the 100 problem instances that we tested that had 127 variables, none of the quantum computers sampled the optimal solution. And this is consistent with what we saw with the MPS sample distributions. However, for both the 116 qubit and the 127 qubit instances, the optimal solutions were always sampled at least once by the IBM quantum hardware. Lastly, I want to note that although we did not touch on this in this study, based on the previous studies that we've done on these problem types, we know that D-wave quantum annealers perform better for sampling these problems than QAOA implementations. Even with this improvement of being able to find good QAOA angles using transfer learning and going to higher P, it's still the case that D-wave quantum annealers perform better. So we are excited about the use of transfer learning, and we want to look at this more. This seems to be a very, very nice way to efficiently get really good QAOA angles. Like in particular, um, you know, like if you really want to study QAOA in detail, one of the things you can do is just classically compute what the best QAOA angles are up to some precision, you know. Um, but the challenge is, of course, you can only do that up to like 32 qubits. Past that, you have to do some other tricks. Maybe you can use MPS simulations, but then even if you're doing MPS simulations, you still have some reasonable amount of computation that is proportional to the entanglement in the circuit. So probably the circuit depth, although not necessarily. And so that makes it hard to actually do the computation at scale, you know, to learn good angles for very high rounds. You have so many parameters, tunable parameters, so many angles that you need to do a very large number of evaluations on that search space. So, you know, even with MPS simulations, it becomes hard. And, you know, even if you have a quantum computer that you can do the variational approach with, that is also hard because that is compute time that you have to expend. So we're very excited about being able to use something like transfer learning, just classically compute on a pretty small problem instance, and then use that for much larger problem instances. But there are limitations there. There are limitations there as well. For example, you can reach a plateau of improvement in, say, approximation ratio or something like that for a smaller problem instance because the energy spectra is generally smaller. And compared to like a much larger problem instance. So there are limitations, but we're excited about that for future studies. All right, and so here's the arXiv link. If you're interested. We have many, many more details that I did not go into in the paper. And a large number of acknowledgements, use of IBM quantum computing and LANL funding, and also use of the Darwin testbed at LANL for HPC resources for the MPS simulations. All right, and if you have any questions after the talk or in the recording, feel free to email me, and I'll take any questions the audience has now. Thank you.
Yeah, well, thank you for your talk. Let's have some questions. So let me ask one. Uh, it seems that one of the results of this work compared to previous studies is that for this large number of qubit problems, you were able to find better angles. But I don't think you ever compared in your plots how much better did your energies become. So can you give us some sort of a rough approximate number of how much better it got?
How much better the angles got compared to, sorry, I missed that, compared to what?
Well, so before this work, clearly there was a lot of QAOA work in the past. So have you compared the energies that you get with this if one would naively just apply the past work?
Ah, no, no, we did not. Um, yeah, no, we did not. I mean, um, one thing is that um, so these problem instances we did look at previously, and there the way that we computed the angles was with a massive grid search, which is very computationally inefficient. We just didn't know a better way to do it, basically. Um, and so that was just a grid search. And yeah, we didn't actually compare against those angles. That is an interesting point. But there we only went up to 2 rounds. So we just weren't able to go to higher rounds. Um, so yeah, in a sense, that's probably, I think that's why we basically didn't compare against those, just because this technique allows you to allows you to basically access higher rounds, which is pretty non-trivial. So in terms of yeah, there's a lot of work on QAOA training and angle finding, and as far as I know, I don't think that there's a method that we could directly compare against really. So we could have compared against something like variational in the loop machine learning. Use something like a just default like Python, SciPy, Qiskit stuff, Cobilla optimizer, that sort of thing, to do variational learning, on the chip and start at something like random angles. Yes, we could have compared against that. That's an interesting point. I will say, this is not in the study at all, but I have run those experiments, and generally they are much, much worse than this transfer learning. Like this transfer learning is in particular using Julie QAOA, is the only method I have found that gets good angles so easily. Yeah. So yeah, I guess I'm yeah, that's an interesting point. I'll maybe mention it to my co-authors as a potential thing. We could compare against like an in the loop variational optimizer, but but yeah, generally speaking, I think this is pretty much the best angle finding you can do, I think.
I see, I see. Okay, so yeah, thank you. Are there any other questions? Oh, there is one. Please.
Okay. Hi, thank you very much. Well, may I understand that the best answer you found for 16 qubit case apply to almost all samples in larger systems, irrespective of the distribution of randomness?
Yes.
Oh, that's very interesting. Is it because the randomness is just plus or minus type? What happens if you have a distribution of the strength, Gaussian, for instance?
Okay. Yeah, very good point. So first I'll say we haven't actually looked at that. And for example, you could ask the case of like, what if all your coefficients are either all +1 or -1, or some weird distribution, or something that's not binomial. Yeah, we haven't looked at that. Um, so I suspect that at least what I've seen, so like some of the previous studies that have looked at parameter concentration for maximum cut have basically the arguments have relied on the similarity of the underlying structure of the graph gives the parameter transfer quality characteristic. So I think, and I could be wrong, we haven't tried it or looked at it very much. I think it should be independent of the coefficient choices. I think the important part is the underlying graph structure, I think. And something, so like in this plot, something you can see is that left-hand plot has higher order terms, right-hand plot does not have higher order terms. And so I've actually measured this. The best angles here, like where that blue region is, there's a very high overlap. They're not identical, but there is very high overlap there. And so that just shows for like removing or adding higher order terms can slightly change the landscape, but it actually didn't change it that much. So this observation is another example of this parameter concentration. Yes, but yeah, no, that is a very, very interesting thing that we should look at.
Yes,
Yeah.
as you know, I ask this question because by changing the coefficients, the absolute value of the coefficient slightly, then it amounts to the change of gamma or beta in some sense. So in this plot that you're showing now, the coefficients are still plus or minus something.
Yep.
Absolute values remain the same. So
Yeah.
I wondered if the transfer learning works in more complicated case with continuous distribution of coefficients. Well, you haven't done it, but it's an interesting topic, I think.
Yeah, no, that's a good point. It may not work then. That's a good point.
Well, that's close to a comment than a question.
Yeah. Thanks. Yeah, that was a good point.
Okay. Thank you.
Thanks.
Right. I think we had some good discussions, and it's probably good move. Probably let's stop here. And see you all next week.
Thank you.